Hello everyone, this is my first page review of the Accelerated Chemistry Practice Test on gas laws, and I will tell you now that you have hopefully worked through a lot of the test, and I will be posting the answers shortly on the website on the LMS, but I will let you know that all of these questions were taken from the Chemistry Olympiad, so they were intended to be challenging, and if you can do these, I think we're ready to really do any sort of gas law problem, which is great. So here we go. Hoping you'll be able to hear me. I'm hoping you'll be able to see what I do. I'm hoping I won't break too many pencil leads, and I will break this probably into a couple of videos. We have 20 ideal gas law problems, we have 20 gas law problems, and then another 10 reviews, because it is important that we start reviewing for the final, which will be coming up sooner than we know it, as we are almost approaching the end of the year. So, first thing, mass of 560 cubic centimeters of a gas at 0 degrees Celsius in 1 atmosphere is 1.60 grams. Which gas could it be? So if I have a volume, and I have a temperature, and I have a pressure, and I have grams, which I can use to find moles, that looks to me like an ideal gas law problem. So that would be PV equals nRT. Of course, I will need to convert my units, and I want to make sure that my camera is still focusing. It is. So, first thing, pressure, 1 atmosphere. 1 atmosphere in kilopascals is going to be 101.3. My volume is in cubic centimeters. 1 cubic centimeter equals 1 milliliter. So that's 560 milliliters, which means my volume will be 0.560 liters. And I do not know, that's actually what I'm going to try to solve for. Now, if my pressure is in kilopascals, my volume is in liters, my R value can be 8.31, and then if I really want to worry about the units, it's kilopascals times liters over moles times Kelvin, which is the last thing I need to see. Temperature is going to be in Kelvin. 0 is going to be 273 K. Now I just plug in my numbers. This is why gas laws aren't quite as exciting unless we incorporate some stoichiometry. Gas laws, you're primarily just plugging in numbers. So P is 101.3. V is 0.560. N is what we're trying to solve for, 8.31, and 273. My apologies if I seem distracted at times. I have a dog, a rabbit, and 2 cats close by, and they are a little bit distracting. So, and I have a pencil that's not giving me lead like I'd like. All right, so divide both sides by 8.131 times 273. Let me get my calculator. No shame in using electronics as necessary. So 8.31 times 273 is divided by 2. There we go. It started all. Oh, come on. We started already. All right. 268.63 divided by 268.63. Now I have 101.3 times 0.560. 56, that looks about right. Now I'm going to divide that by 2268.63. That is my N. So N equals 0.02500000054. So does that make sense? I need to ask myself. Should I be expecting a small number for moles? I really should, because if you remember at STP, which is actually this is standard temperature, this is standard pressure. 1 mole of a gas is supposed to equal 22.4 liters. This is only about a half a liter, therefore I would expect to have a small number. Always ask yourself, does my answer make sense? Now, molar mass is grams per mole, so the grams I have is 1.6 grams divided by 0.025 moles, and I should get the molar mass, which would be 1.6 divided by 0.025, 64 grams per mole. Oxygen can't be oxygen because oxygen is 32, 16 plus 16. CO2 is 44 because it's 12 plus 32, 44. Chlorine is 71, 35.5 plus 35.5. Sulfur is 32, oxygen, 1 oxygen is 16, 2 oxygen is 32, 32 plus 32 is 64. Therefore, our most likely candidate for the gas is letter C. Alright, on to number 2, which I think should still show up on my page, and I can see that it does. Sorry, I have to stand up each time that I need to check. Alright. 3 balloons are filled with the same number of atoms of helium, argon, and xenon respectively. Which statement is true under the same conditions of temperature and pressure? Now you'll remember, under the kinetic molecular theory, all gases occupy the same volume and they exert the same force on the sides of the container. All gases behave identically. So, they would not contain the same mass because you have different molar masses, but each container would have the same number of atoms. Same number of atoms. Each of these atoms has a different mass. That's what I'm trying to say. So they would have a different mass. Therefore, A can't be true. All balloons have the same volume. Well, we do know that that would definitely be true, but let's take the others two also. Density of the 3 gases would not be the same because the masses are different, even though the volume might be the same. Average speed of the different types of atoms is the same? No, because if remember we talked about Graham's law. Graham's law, larger atoms will travel slower, smaller atoms will travel faster. The reason why is because both exert the same amount of force. If a xenon atom is hitting the side of a container, it'll hit with the same force as helium. How is that possible when helium has an atomic mass of 4 and xenon has an atomic mass way higher than that? I don't have a periodic table in front of me, although I should probably get one for the remaining problems. But the reason why is because helium travels much faster than xenon. And if I can look, I'm going to have to get my periodic table just so that I am ready for this in the future. Okay, so with that said, and I just bumped the camera, but you'll still be able to see anything. All balloons would have the same volume in this case. As we know, all gases occupy 22.4 liters at STP. 1 pencil down. My apologies if you see a bit of a jump there. I had a bug order come in that I had to respond to. So, we're on to problem 3. A 0.239 gram sample of a gas in a 100 milliliter flask. So I have a gas, a gram mass, I have a volume, I have a pressure, I have a temperature. This is another ideal gas law problem. Turns out that the Chem Olympiad has a lot of ideal gas law problems. But what is this doing? This is forcing us to convert units, which is important. Remember about our temperature, grams to moles, or actually in this particular case, moles to grams. All of this is very important and relevant information. Keeping our units consistent also. So pressure in this case, let me just make sure I'm still focusing properly. Yep. Alright, so pressure is given as 600 millimeters of mercury. And then I have to do my conversion. So my preference is to remember one ideal gas constant, 8.31 kilopascals times liters over moles times Kelvin. That's my preference, so I'm going to turn all of my pressures into kilopascals. So that'd be 101.3 kilopascals over 760 millimeters of mercury, which then means I have 600 times 101.3 divided by 760 is 79.97 kilopascals. My volume is milliliters. I have to convert it to liters, 0.100 liters. My N is what I'm trying to solve for. My T will have to be converted, so that's 14 Celsius plus 273, which equals 287 K. 287 K. Okay, so I have my pressure in the right units. Now I also might want to think, this is normal atmospheric pressure, this is lower. This is normal atmospheric pressure, this is lower. That means I did my conversion properly, or at least is a good check on that. So now it's PV equals nRT. Pressure is 79.97. V is 0.100. N is what I'm trying to solve for because I have a gram value but I don't have a mole value. 8.31 and then 287 for the K. So 8.31 times 287 is 2,384.97. So now I divide 79.97 times 0.1 divided by 238.97. Very small number here. So my number of moles is 0.003353. We'll leave it at that. Moles. I have a gram value, I have a mole value. So to find my molar mass, it would be 0.239 grams divided by 0.003353 moles, and then I'll get my gram per mole value. So 0.239 divided by 0.003353 equals 71. All right, so if I have my handy dandy periodic table, which I happen to have in the back of the textbook I often use. I'm not sure how well this will show up, but if I look at chlorine, chlorine is Cl2. Chlorine is actually probably my candidate. Nitrogen is 14N2. Krypton is 83.80, definitely too far off. And xenon is 131.30, also rather far off. 71 looks and sounds to me like chlorine because the gram molar mass for chlorine atoms is 35.5. Multiply that by 2 and we have our 71 grams of a molar mass. So that would be chlorine. Now let me see if I can... My apologies for another pause there. I had actually another bug order come in, so I had to take care of that. But let me get my bearings again. I have my pencil. So, sample of neon gas has a volume of 248 milliliters at 30 degrees Celsius and a certain pressure. What volume would it occupy if it were heated to 60 degrees Celsius at the same pressure? So pressure staying constant here. If pressure staying constant, not an ideal gas law problem necessarily. I have a volume, I have a temperature. I have to find a volume and I'm given another temperature. That looks a lot like a V1, 248 milliliters, T1, 30 degrees Celsius. Then we're asking to find a V2 and T2, would be 60 degrees Celsius. Of course, I need to convert my Celsius to Kelvin. So 273 plus 30 is 303 K. And this is 333 K. So now I've converted my Kelvin. That is absolutely necessary in every single gas law problem, regardless. Do I need to change volume to liters? It's not absolutely necessary unless we're talking about the ideal gas law. Because remember, ideal gas law, your ideal gas law constant requires liters. Charles' law does not require that. So I could get away with not converting this. Would it hurt me if I went milliliters to liters, then found a liter value, then went back to milliliters? No, I mean my answer is in milliliters, so I would have to do that. Could I just go straight milliliters to milliliters though? I could also do that. So let's do 248 over 303. Those are my initial conditions. V2 over 333. I can cross multiply. 303 V2 equals 248 times 333, and then I would end up dividing by 303, dividing by 303. That means my final answer will, or my final volume will be 248 times 333 divided by 303, 272.55. So if I'm rounding up, that would be 273 milliliters. Now, technically, even though this is the Chemistry Olympiad, I should only have, you may notice, I should only have two significant figures. So Chem Olympiad has some explaining to do in that particular case. Number 5 is a manometer problem. Again, the difference in pressure between the inside and the outside is reflected in the difference in the height of the mercury column. If the pressure is pushing more here, then it's going to push it up higher on that side. If the pressure outside were higher, it would push it down the other way. Now let me just make sure this is all fitting on the screen. It is. Okay. So, the pressure, atmospheric pressure, which is on the outside, is 735 millimeters of mercury. The pressure inside is 44 millimeters of mercury greater than that. So really all we are doing is 735 plus 42. It is 777 millimeters of mercury. The answer is D. And I didn't mark up here what this one, V2, 273, that's B. Okay, with that we have finished the first side of page 1, and I hope I can steam through the next one. Let me just balance up my come on. Balancing up the camera, but there we go. So helium, you may not be aware of this, but helium is very much a gas that comes out of the ground. It's a product of nuclear decay. Radium, for example, decays into radon. Many radioactive elements undergo alpha decay, and that helium is trapped underground. So we actually do get our helium underground, just like we get our natural gas or methane. So, helium is often found with methane. How do the diffusion rates of helium and methane compare at the same temperature? Helium, so I'm trying to do the rate of helium compared to the rate of methane, which would be the same as the square root, this is now Graham's law, the molar mass of methane, so it's rate A over rate B equals the square root of the molar mass of B over molar mass of A, in this case helium. That means molar mass of methane, which is 16, divided by them, because it's 12 plus 4, 1 times 4 is 4, 16 grams over 4 grams, which is helium, 16 divided by 4 is 4. Square root of 4 is 2. So helium diffuses twice as fast as methane. That is the first problem. Now let me see if I can adjust. Getting a little issue with fitting everything on the screen, but I'm hoping this will work. So next one. Let me move it up a little more. A gas has a volume of 6 liters at a pressure of 0.80 atmospheres. What is the volume if the pressure is changed to 0.20 atmospheres at a constant temperature? So again, in this particular case, we're dealing with volume, we're dealing with pressure. We're trying to find a volume, and we have a pressure change. So that is a Boyle's law problem, which means my P1 is 0.80. Again, with Boyle's law, as long as I'm consistent with my units, I don't need to change it into kilopascals. Would it hurt me if I went from atmospheres to kilopascals and changed both of these? It would give me the same answer. It doesn't really matter as much the units, as long as I'm consistent with Boyle's law or Charles' law or Guy-Lussac's law or the combined gas law. As long as my units are consistent, I don't have to do any conversions. It's only with ideal gas law, because of that ideal gas law constant, that I would have to change it. So 0.80 atmospheres, and this is 6 liters. Now we're changing the pressure to 0.20 atmospheres. What did I do there? The temperature remains constant, and my new volume V2. So P1 V1 equals P2 V2. Divide this by 0.20. 0.20. So we have now 0.80 times 6 divided by 0.2. 24. Now think, temperature's remaining constant. I'm lowering the pressure. If the pressure goes down, the volume has to go up. So this one actually does make sense. So my V2 equals 24. I plugged in liters, I get out liters. If I plugged in milliliters, I get out milliliters. I get, instead of, this would be 6,000, I get 24,000. So this case, though, I did use liters. That's my answer, is 24. Which element is a gas at 25 degrees Celsius and 1 atmosphere pressure? This was not such a brutal problem, I hope, because we only know a couple of gases that are actually on the periodic table. Sulfur is a yellow solid. Silicon is a metalloid. Phosphorus is a very reactive solid. The only one that is a gas at 25 degrees Celsius would be chlorine, which is a fairly dangerous gas, but a gas nonetheless. Now I think with that I'm getting short on space. I have to slide up. See if I can fit 9 and 10. Not quite. A little bit higher. Alright, well, we'll at least look at 9 right now. A sample of oxygen gas and a sample of an unknown gas. A sample of oxygen gas and a sample of an unknown gas are weighed separately in the same evacuated flask, which means a flask where all of the air has been removed. Use the data given to find the molar mass of the unknown gas. Assume the experiments are carried out at the same pressure and temperature. So what do I have? I have the mass of the evacuated flask, mass of the oxygen, mass of the flask plus the unknown gas. Alright, this is what I need to do first. I need to take the mass, find the mass of the oxygen. So 125.1 minus 124.46, 0.64 grams of oxygen and 125.34 minus 124.46, so that's 0.88 grams. Now, what do I need to know in this particular case? any amount of gas, the number of moles, this is Avogadro's law, the number of moles of any gas are going to occupy the same amount of volume at the same pressure and temperature. So if I find out how many moles of oxygen I have, I automatically know how many moles of this other unknown gas that I have. So what would I do? I would change grams to moles, and this, don't forget, instead of 16, it's 32 grams. So now I have 0.64 divided by 32. That means I have 0.02 moles of oxygen. I would have exactly the same number of moles of this unknown gas. So that's the grams, and then divided by the moles, I'll get the molar mass. So 0.88 divided by 0.02, my answer is 44 grams per mole, which means if you really know your gases, that's probably carbon dioxide. That's one of the ones that has a molar mass of 44 grams per mole. Now the very last one at the bottom here, which pair of gases has the same average rate of diffusion at 25 degrees Celsius? The 25 degrees Celsius is just to establish that these are two things that are gases at this temperature, although all of these actually are gases. If you remember, this is another Graham's law problem. So the Graham's law states that basically gases with the same molar mass are going to have the same rates of diffusion. So helium and neon, helium is 4, neon's around 20. That can't be, they can't be equal. Nitrogen is going to be 28, oxygen is 32, fairly close, but maybe not close enough. So nitrogen's here, 2 nitrogens, 28, 28 plus 16 is going to be 44. And carbon dioxide, we just said earlier, is 44. And then ammonia is 17, and hydrogen chloride is 36.2. So it would be this letter C. Alright, that is the first page. I think I'm going to stop this video. I will edit it and load it up, and then I will continue with pages 2 and 3, which has concepts to remember. Some review also. So this is the first page of the practice test for accelerated chemistry.